Hi, it's me, Paula, the math tutor. In this video, we're going to discuss continuous random variables and we are going to define what a probability density function is for a continuous random variable. So for that, first we are going to remember what a continuous random variable is, then we are going to construct the idea of what a probability density function is and give a definition. And finally, we are going to do an example where we calculate probabilities using the probability density function. So let's begin. In a previous video, we talked about continuous random variables when we introduced random variables. You can check that video if you want to. But in the case of continuous random variables, the main difference between them and a discrete random variable is that in a continuous random variable, the variable can take any value in a specific interval of numbers. We have infinite many numbers that the variable can take between two values. So we can't just pick one and calculate the probability of that, because the probability of a random variable to be exactly equal to something, it's always going to be zero. Think about it this way. Let's say your variable is the weight of apples, and you want the probability of getting an apple that is exactly 200 grams. That's going to be actually impossible to get. You may get an apple that's close to it, but getting an apple that is exactly 200 grams, it's probably impossible to get. Even if you manage to get a perfect apple with 200 grams, the measuring tools you have are going to have errors. Let's say you have a scale, and the scale gives you the weight with an error of 0.1 grams. It's a very good scale. But still, if you weigh your apple and it's 200 grams, you'll never know if it's exactly 200 grams or 200.001 or 200.005 or 200.009 or 199.9. You get the idea. So getting a continuous random variable to be exactly something, the probability of that is zero. Meaning that to calculate the probabilities for continuous random variables, we are always going to be calculating it in an interval. We want the probability of x being between a and b, for example. And an important note here, because the probability of x being equal to something is zero, it doesn't really matter when you're calculating the probability of x being between a and b, if it's larger than or equal, or smaller than or equal, or just larger or just smaller. All of the combinations you can make of that are going to be exactly the same, because what we want is what's in between, not what's exactly in one value. And with discrete random variables, we were able to define the probability mass function, but that gave us the probabilities for exactly every value that the variable could take. Because the continuous random variable, we can't work like that. We need to introduce the idea of the probability density function. And in this point of the video, I'm going to give you the idea of why the probability density function works. If you don't want to see that, if you're not interested in that and you just want to go straight to the definition, that is okay. So you can check the timestamps in the video and go straight to that. But now we're going to discuss the idea behind the probability density function, why it makes sense, why it works. But again, if you want to go straight to the definition, that's completely fine. If you don't need the idea and you just want to go straight to calculating things, go ahead, check the timeline and you can skip this. But let's go to the idea behind why the probability density function makes sense. When we were working with discrete random variables and we wanted to calculate cumulative frequencies, meaning that we want to add the frequencies of something happening and the things before that happening, we just needed to add them. That was as easy as that. If you want the cumulative frequency up until a certain point, you just add everything that came before until then. But because we can't do that with the continuous random variables, because we don't have the specific probability values for each of the x's, and because we have infinite many of them, we are going to borrow from physics the concept of density. Imagine you have a metal rod and you want to calculate the mass of it. The mass of the rod is going to be equal to the density times the length of it. If you want the mass of a tiny sliver of that rod, let's say of a length of dx, then the mass of it would be the density times that dx. And yes, dx, it sounds familiar, because when variables get continuous, they can also get differentiable. We're going to start using calculus for this, because as we are working with a continuous situation, the variations, how this changes, the rate of change, and how it accumulates, it's going to be very easy to describe with derivatives and integrals. So we're going to translate what we did with discrete to the continuous realm, and for that we are going to need calculus. We know that the probability of x being between little x and little x plus dx is going to be close to our probability density function, the one that's giving us the density of the probabilities, times that dx. So if f of x gives me the probability of a sliver, then finding the cumulative frequency, let's call this capital F of x, which is going to give me the total mass from the absolute minimum to that value of x. It's going to mean that I'm going to accumulate all those little slivers from the minimum to that value of x. And that is not other than calculating the integral between the absolute minimum to that value of x of the function that we call density function. Another way of seeing this is that the derivative of the mass is going to be this function, which is my density. And that is the idea behind the probability density function. We generate a function that's not going to give me the probabilities. That's very important. The values, the f of x, are not the probabilities for x, are the density, meaning that it's giving me how dense the probability is around that point. And with that, if I use the integrals, I can get the probability. So if you get a probability density function, you can calculate the integral between two values in an interval, and that is going to give you the probability of x being between the first one and the second one. My definition for the probability density function is then that if I have a continuous random variable x on a domain, let's say between a and b, two real values, the probability density function is going to be a function, let's call it f of x, such that the probability of x being between a c and a d, any two values in that interval, is going to be the integral between c and d of f of x dx. It's the area under the curve of that function. Because this is a probability density function and it's going to give me probabilities by finding the area under the curve by integrating it, we need to ask this function a couple of conditions. First of all, the total area in its domain in between that a and that b needs to be 1. That is going to be the total probability. Because it is a probability, I need it to be 1. And then the other thing I need to ask it is, because it's going to be representing density of probabilities, it needs to be always larger than or equal to 0. I can't have negative values of the density of a probability. Let's try an example then. Let's say I have f of x equals 3 over 8 x squared, defined between 0 and 2. Let's try to see if this could be a probability density function. First of all, if we want to check that this could be a valid probability density function, we need to check that all the values that f of x can take are positive or 0. And they are, because I'm squaring x and they're multiplying it times 3/8, which is positive, so they're all going to be positive or 0. And now we need to check that the area under the curve in its domain, it's 1. So I need to calculate the integral between 0 and 2 of 3 over 8 x squared dx. And here, let's do some calculations. First, let's take the 3/8 outside, and now we have the integral between 0 and 2 of x squared dx. The antiderivative of x squared is 1 over 3 times x to the power of 3 cubed. So at the end, we are going to be evaluating 3/8 times 1/3 x cubed in 2 and in 0. If we simplify those fractions a little bit more, we get 1 over 8 x squared, and we need to evaluate that in 2, in 0, and subtract. Then we are going to get 8 over 8 minus 0, and that is 1. So the total area is 1. This function meets the conditions to be a probability density function. Now, let's say we have x, which is the random variable that's associated to this function, and let's calculate the probability of x being between 1 and 2. For that, we want the area under the curve between 1 and 2, so we want the integral between 1 and 2 of our density function. We already know that the primitive of this function is 1/8 x cubed, so we're going to be evaluating 1/8 x cubed in 2 minus that in 1, and if you do that, you end up with 8/8 minus 1/8, which is 7/8. That is the probability of this random variable being between 1 and 2. And this is it for this video. In the next one, we are going to be discussing the measures of center and spread of a continuous random variable. Again, if you want to review what we did with discrete random variables, you can go to that series of videos and check it out. I'll see you in the next one. Bye bye!